This has been on my list of projects for a while, but I never realized how long this would take me and how involved it was going to get. If you ever thought about how to reuse the sensor in the scanner of a printer, well, this is the video for you. Besides, I had a bunch of these sensors and no idea how to reuse them, so I'm going to share everything I've learned so far about these sensors. At their core, these modules are just a line of photosensitive CMOS sensors. I'm going to use a microcontroller to interface with them, and I recently picked up the STM32 chip to play around with. My reason is that other than learning how to program a new microcontroller, it would be easier to use a 3.3 volt micro for a 3.3 volt sensor, rather than risk using 5 volt signals. Now, not to say you can't use an Arduino for this, but you might have to use logic level shifters. So I want to talk about three main things: pins and signals, timers, and analog data. But first, maybe a little bit of background would be nice.
So these contact image sensors, as they're called, use CMOS technology. And CMOS technology is actually built into the PCB, built onto the PCB. It's very easy for manufacturers to build these types of photosensitive sensors. What we had before this was CCD sensors. Now these CCD sensors stand for charge coupled device. Now, CCD sensors are not used that much today, but they are still common because their quality is arguably better than the CMOS sensors. They provide much sharper images with better light sensitivity than the CMOS sensors. And so these are still used, but they're not as common as the more easy to manufacture and cheaper CMOS sensors. I'm trying to make a video here and this dude just keeps meowing. These sensors are more expensive to manufacture and also use more energy. They use more circuitry on the outside to amplify the signal that they receive. Unlike the CCD sensor, the CMOS sensor has amplifiers at each individual pixel. And so it can do local processing of the image or of the pixels. Now each of these sensors have their advantages and disadvantages, but they're pretty similar. It's important to note, however, that before we even had either of these two sensors, we had the vacuum tube sensor. So the same kind of tube that's in your CRT TV to create an image on the screen, well, that same tube can also be used to detect the intensity of light across an image. And because it can do that, and when it does that, as far as I understand, the current varies, and that current can also be sensed and processed as pixel data. So that's how they did it back when they didn't even have this technology. They just used tubes. Now, one of the more interesting things that I found out when I was doing research on both the CCD sensor and the CMOS sensor is that a lot of people liked to go into scanners and either take the CCD sensor or the CMOS sensor that was in there, and they would assemble it into a full camera, a line scanning camera to be precise. And when I did more research on the line scanning camera, I found that it was very commonly used in manufacturing, because when things are on a conveyor belt, they often use these line scanning cameras to ensure quality control.
With the ability to detect light, you can arrange this kind of setup with lights, and since the sensor can detect your finger's shadow, people have been turning any kind of surface into a touch screen. Now, I'll be honest and say I'm not that experienced, and the furthest I've come is making a simple light detector with these image sensors. I still have to figure out how to clock out pixel data from the analog signal. Let's talk about the pinouts now. I think the best way to figure out the signals and pins is to have the logic board connected to the sensor while you probe everything. If you don't have the logic board, well, there's one method I came up with to help me guess the pinout, but it's not reliable. I'll talk about that later.
To start out, I want to talk about this specific sensor. And that's because I've already figured out all the wiring and all the signals that are needed to power this thing and make it work. So I dedicated my time to figuring out everything I could about this in order to understand down the line any other sensor like it. And I just want to share this knowledge. So maybe if you come across a similar sensor, but it has differences of its own, then you won't have a hard time to try to decipher the pinout. First, we're going to talk about every signal that's necessary in order to power this and what I've learned from working with this sensor. And then we'll move on to a completely brand new sensor, and so I can guide you step by step through that. If you find a concrete datasheet for the sensor that you're using, well then by all means follow it to see the pinouts. But I'm just saying in my case, those datasheets that I found were not relevant to the sensor that I was looking at. And so I just used them as a guide to see what common pinouts there were between different types of sensors. And that guided me to understand the layout of the pins a lot better. But that's just general information that you should use as a guide if you just can't find the relevant specific data sheet for your sensor. So the pinout is as follows. The first pin being the plus 3.3 volts for the LEDs, and pins 2, 3, and 4 are for the LED's common negative terminals. Now onto 5 is just ground, and 6 is the analog out. 7 is the plus 3.3 volts that actually powers the board. 8 is another analog out, which actually surprised me because I never expected that. It turns out that this board is actually divided into two sections. And so one section is our first analog out, and another section is our second analog out. And that's what I found just through trial and error by power cycling this board and probing these pins. Pretty interesting. I never expected that. Anyway, pin 9 is ground. Pin 10 is our pulse signal. Pin 11 is our clock. And finally, pin 12 is ground. So as you can see, the two most important pins on this sensor, other than actually powering the sensor, is the pulse signal and the clock. And I want to specifically talk about these two signals because they're very important and they have some traits that are quite interesting. Now, when I was power cycling the logic board that was connected to this sensor in order to power it and probe the pins, I noticed on the analog out pin there was 1.1 volts at a range of 2.6 kilohertz to 800 hertz. And at first I thought this was the starting pulse. And it confused me greatly because the actual starting pulse likes to be at 800 hertz, and that's what I measured on the starting pulse signal. However, the whole point in me writing this down and actually telling you what the signal was when I probed it while it was being powered is so you can know what to expect when you're taking readings off these pins. It's important to know what you measure in order to identify that this pin is actually the analog out. So if you're reading 1.1 volts at a range of 2.6 kilohertz to 800 hertz, then most likely that pin that you are probing is the analog out pin. So let's talk about the pulse signal for a little bit. Now, when I first measured this signal, it was a negative 0.1 to plus 0.1 value on my multimeter. And at first, when I measured this, I thought this pin just didn't do anything. I was very confused why I was getting that reading. And the only reason that I figured out later that this pin that I measured the signal on was the pulse signal pin was simply because I thought of using different methods to viewing the signal on that pin. Notice how I said I first used my multimeter to view this signal. Well, see, that was a mistake because as you can see, later I found out that this signal likes to have a very, very short duty cycle. That signal is extremely short. And so as a result, my multimeter had a very troubling time to basically show me that signal. So after that, I even tried to use the STM32 microcontroller I had at hand, and I captured via the serial monitor plotter the signal that was coming out of that pin. And that finally confirmed that that pin was the pulse signal pin. And it was just a matter of looking at the signal with the right methods. So take that into account when you're reverse engineering pins in the future, whether it be for this sensor or any other thing. Now, I learned pretty early on that the clock frequency is actually pretty flexible. But that obviously depends on your specific sensor, because these sensors can typically range anywhere between 1 megahertz to 8 megahertz. And this one was 3 megahertz. And if you went below that frequency, even just a tiny little bit, then you would not have an analog output. And so for this specific sensor, it liked to stay at either 3 megahertz or above. And I actually tested this sensor to probably around 8 or 9 megahertz, and it, worked just fine. And I'm sure with a higher clock frequency, you could probably get away with higher or lower starting pulses. So timers and microcontrollers were kind of a learning curve for me, so excuse me if I'm not explaining everything correct here, but everything that I wrote down here is for myself to understand and manipulate these values to get a certain frequency. And it's actually more simple than you think. So let's start off with the clock. The clock in this microcontroller runs at 72 megahertz naturally. And then you have a prescaler. That prescaler is simply just a value that divides that main clock into more manageable sections. And then you have the auto reload register. And all that is just a value that the clock counts up to or down to. And then finally, you have your desired timer frequency. And that's what you see at the output of your pin. And so now we just have a simple formula to calculate the desired timer frequency that we want out of a certain pin. Here, I'll give you an example. Say we wanted to calculate a frequency of 800 hertz, such as in the case of our starting pulse, which is, of course, 800 hertz. So we start off with the main clock, and that being 72 million hertz. We divide that by 800 hertz, and then we get a value of 90,000. Now, in order to get our desired timer frequency of 800 hertz, we need that value to be 90,000, but that value is calculated by the prescaler and the auto reload register in the code. We have to get that value by modifying the values of the prescaler and the auto reload register. You're not limited to any combination of numbers, you're just limited to a range of numbers that you can play around with the prescaler and the auto reload register. And of course, this is limited by the bit resolution. So if we had a prescaler of 2 and we had an auto reload register value of 45,000, well, then we would have our value of 90,000, and therefore our frequency at the output would have to be 800 hertz. And it turns out that's exactly what you get. This can also work with the auto reload register being 2 and the prescaler being 45,000. It really doesn't matter.
All right, so I wanted to jump into the code and just explain some of the stuff in here. So this is the clock timer, obviously, and this is the start pulse timer. And like I mentioned before, you have a prescaler right here, and you can modify that prescaler. And you have an auto reload register as well, which is the overflow value, which you can also change. And so with these two numbers, you can change the frequency on this pin right here. And this function over here, as far as I understand, it changes the duty cycle of the signal. So if you want to change the duty cycle, you just change this number. Down here is where I manipulate the analog signal coming out of the sensor. Basically, what's happening over here is I'm forcing the microcontroller to sample any analog data from PA1. And I'm doing this over and over and over again. The amount of times that I do this depends on this variable up here, and so I can increase or decrease as necessary. But basically what we're doing here is getting an average value for the analog data that's coming off of the sensor. And what we're doing with that average is comparing it to like a certain value that you choose. And this value might be different for you, so you have to look in the serial monitor and determine what that value actually is, or what that threshold would be, right? And so if the analog data is above a certain threshold, then it will turn on an LED, and that's as simple as as it gets. The reason we are averaging the analog signal is because we need a steady value to work with. This is actually the raw analog data coming off the sensor. Notice how when I shine my flashlight on it, it looks like it's not detecting anything because the signal is just too chaotic. Averaging the data helped me choose a nice threshold value for this simple light sensor, but obviously you can do more than just that with this.
All right, let me rewind a little bit. So I had a bunch of success with this sensor over here. It was really simple to interface with once I knew the correct pinout. However, to solidify my learning experience, I wanted to move on to a different sensor. So I moved on to this one, and this one proved to be a lot of trouble. So this sensor over here has 12 pins. And I figured out all the pins because I had the logic board connected over to it, made it really simple and easy. And then when I wanted to move on to this sensor, I decided that since I didn't really have a logic board for this sensor to power it up and stuff, I was going to have to work with it blind. And so to help me out a little bit with this sensor, I decided to gather as much data as I could on this one with the 12 pins. By the way, so this one has 12 pins, right? And this one had 14 pins. And I thought this was going to be really simple. So what I did is these 3 tests on this 12-pinned sensor over here. And I got a bunch of data. And actually, it was fairly interesting because I could accurately figure out and pinpoint the VCC pins, so the power pins and the clock pin and the starting pulse pin. And I thought this was going to apply to every sensor out there, but I was wrong. So what ended up happening is that when I tried these 3 tests on this sensor, I didn't get the right pin out. And the whole reason for that is because this contact sensor uses differential signaling, and this one does not. And basically what that means is that this sensor here does not reference to ground for the output, and this one does. And that makes a huge difference because for one, it adds more complexity to this sensor because you have to add additional signals. So with this simple 12-pin sensor, the only thing you had to do was power it, put in a clock signal, and put in a starting pulse signal, and then you got an output. Easy peasy, right? But this sensor, no. You have to put the starting pulse, the clock signal, you have to power it. You also have to provide 2 signals to 2 different pins, and one of those signals has to be the inverse of the other one. And by the way, this pinout over here is the pinout for this 14-pin sensor. And so in conclusion, I think you should stick to the very simple contact sensors with fewer pins. If you are working with fewer pins, that's generally a good sign that the sensor is more simplified, and you won't have to do as much work to get it going. If you're working with like a 14-pin sensor, then you might have to provide it with some differential signaling. It might add complexity, and you might start pulling your hair out with this sensor. So just keep that in mind. And one more thing, so just to reiterate, these 3 tests will work on very simple sensors, so 12-pin sensors, but these 3 tests will not work on the 14-pin sensor, so the more complicated sensor, because they have more pins and you can easily get lost and misdirected with these tests using them on this sensor. So just a bit of caution. So basically, this is what it comes down to for the 14-pin sensor. So I put in the clock, and I have the starting pulse, and I power it. But when I hook up my probe to pin 11 and pin 12, and this is the thing about the differential output, is that you are not referenced to ground. So you connect your probe up to pin 11 and pin 12, and this is different than, say, the other sensor, because with the other sensor, you would have just one analog output. And then you would connect your probe up to that one single pin and then reference that to ground. Here you're not referencing to ground, you just connect up to pin 11 and 12 and you have your differential output. But the problem here is that you will not get anything on pin 11 and 12 if there is nothing on pin 8 and 9, because those are where the inverse signals go into. And just to add to the confusion, I don't know what the hell is on pin 5. There's this like weird 1000 hertz frequency with a plus and minus of 50 millivolts on it. And this I measured when it was in operation, when the sensor was actually connected to the printer and stuff. But yeah, I don't know. I'm still trying to figure this out myself. I'm trying to maybe figure out if I could bypass the inverse signals. Maybe I could connect them up together and put one signal through both of them. I don't know. Any smart people out there, tell me what I could do to get some kind of output here, or maybe what things I could try. But yeah, that's as far as I came with this project. I'll probably revisit this in the future, but you can already tell how complex this all is. The fact of the matter is I'm working with a simple 2-channel function generator, and since it's on the cheaper side, I don't believe it can do differential signaling. Maybe if I had a function generator with more channels, I could whip up an external circuit that would probably be like a 1-transistor inverter type deal. And then I can generate those inverse signals to put into this sensor and maybe get a differential output. But as you can already see, that adds way more complexity than this simple sensor, you know? I think I'm going to stop here just for the sake of my sanity. Over the course of about a week, I just learned about so many different things, not only how to interface with these sensors, but also how to work with timers and microcontrollers, and how to program the STM32, which is great because then I can use it for future projects, so I'm really happy about that. So, like always, I hope you learned something, and I hope you enjoyed watching, and I'll see you in the next one.